All right, hello again. So let's continue talking about uh, what a spectral norm is and what a spectral radius is, just to continue our course in multivariable control. Uh, my name is Professor Lajimi, and I got my PhD in Systems Design Engineering from University of Waterloo, from the Department of Systems Design Engineering. Got my master's in Mechanical Engineering from École Polytechnique Fédérale de Lausanne. All right, let's talk about a spectral norm and the spectral radius. The spectral radius is the largest eigenvalue, and a spectral radius looks at what happens along that special direction. The spectral norm looks at worst case scenario over all directions. So, and a spectral norm looks at all possible directions, meaning that a matrix can strongly amplify some directions, even if all eigenvalues are very small. Eigenvalues describe asymptotic behavior. Singular values describe instantaneous gain. Again, eigenvalues describe asymptotic behavior, but singular values describe instantaneous gain. A spectral radius predicts stability. A spectral norm measures gain. So one talks about gain, the other one talks about stability, and confusing the two leads to serious design errors when it comes to designing your control system. Commonly used matrix norms include, let me just continue, Frobenius norm, sum norm, maximum column sum norm, and maximum row sum norm, and induced two norm. Just so you know, there is no single correct norm in mathematics. And engineering choice depends on interpretation, but for energy and worst case scenario, worst case amplification, induced norms are small, are most meaningful. The induced norms or two norms are most meaningful because of their relationship with energy definition. Sorry. All reasonable matrix norms differ only by bounded scale factors. The choice depends on interpretation and convenience. So as you know, we also talk about convenience here. It's not just about interpretation, but it also depends on convenience. Choosing a norm is like choosing units. It changes numbers, not physical conclusions. Again, pay very close attention to what I just said. Choosing a norm is like choosing units. It changes numbers, not physical conclusions. And the key result for this chapter, or essentially section, is we primarily use the induced two norms, and that was the sigma bar g. The sigma bar g represents the largest output amplitude produced by any unit energy input direction. So again, it matches the energy interpretation from the two norm of vectors. Let's think about this mechanical intuition. Sigma bar g represents the largest output amplitude produced by any unit energy input direction. For the counterexample above, bar sigma is equal to 100, which captures the true gain of the system. While, for example, in that example, this is the latest example from last video lecture, the eigenvalues are said zero gain, because that's what they said. They said we have zero gain, we don't have any gain. The output should be zero, but then singular values reveal huge gain. We have the sigma bar g equal to 100. Latest example we had from latest video lecture. So eigenvalues may hide worst case scenario, worst case amplification. Singular values expose it. All right, let's talk about now singular value decomposition. Let's start our discussion on singular value decomposition. Let's fix a frequency omega. That's what we said. We said we're going to fix the frequency omega. We are going to look at a snapshot of the system. And then we're going to compare the steady state response. The fix frequency omega, so we fix the frequency at a omega, and then the frequency response becomes gj omega. So gj omega is a constant L by M complex matrix. So a constant complex matrix. For simplicity, let's denote that by G. So when we say G, it's J omega. So we freeze the time by fixing frequency. Once frequency is fixed, there is no longer dynamics. It is geometry in complex space. It's a static mapping. So this is the same. Just show if you, for students who are working on mechatronics projects, this is the same idea behind phasors in circuits and vibrations. Dynamics disappear, structure remains. All right. Now let's look at the definition of singular value decomposition. Any matrix G admits the factorization. G equals U, capital U, sigma V, H, V superscript H. U is unitary output directions. Sigma is diagonal with non-negative singular values, sigma I. And V is a complex matrix. M by M is unitary output directions. So the SVD separates directions or rotations from gain or scaling. Right? So it's why it's called decompositions. Let me go further, and then as we go further, you're gonna understand why it actually is true and why it works. Although you can take a look at any linear algebra textbook, and then you can find a proof for that. This works, this G equal U capital U sigma, this thing works for any matrix, a square, rectangular, tall, wide. V, output direction, how you push. All right, it describes how you push. Sigma is how much it responds. And U, capital U, how it shows up at sensors. All right, so let me stop here, and then we're going to continue in next video. Think about this, and we're going to come back to this thing. Thank you very much.